Hello everyone, my name is Gabe. Today I'm going to be doing an introductory mathematical exploration to dynamic hedging. I have in mind an undergraduate student who has some background in finance and is being exposed to the binomial pricing model for the first time. I want to give them a view of how this model can be actually used in the real world. The big idea I hope you get from this video is that we can respond to conditions in the market and effectively take away a lot of the downside risk to investing. Okay, let's come up with a situation where a financial services company might need to use a dynamic hedging strategy. Here we have a financial services company called eGape Financial. The client wants to invest $100 in the stock market. The client is willing to pay an extra premium or a small extra amount of money to guarantee a minimum return on the $100 if the stock market does not perform well. And I, as a financial services company, want to provide this service to the client. Okay, two key questions come up. First, how can eGape Financial provide the guarantee, i.e., how can we hedge our risk? And two, how much will the hedge cost? What is a fair price to charge our client? Let's construct a financial environment so we are working with some real numbers here. Let's say we have a stock market portfolio that keeps track of a stock market index like the S&P 500 or Russell 2000. We can borrow or invest in bonds at the risk-free rate of 4%, and the client wants his money back in 1 year and wants a guaranteed return of 2%. We should consider what we need to pay our client at the time of expiration. Mathematically, I formulated the payout to the client as the maximum of what ends up happening to the stock market and the initial investment with a rate of return of G. We can write our maximum as such to show the different components: investment in stock market and the guaranteed component, which I've labeled V of T. To cover the stock market component, we can simply use the client's $100 to purchase the stock market portfolio at time zero, and we need to figure out how we can mechanically cover the guarantee component and how much it will cost us to use our strategy. We need a model. We can start with a simple model that only has two possible outcomes. It goes up or it goes down. We determine how far it goes up or how far it goes down with these factors U and D, which is controlled by a parameter sigma. Sigma measures how far up or down the stock portfolio can go. You can think of this number as measuring the volatility of the stock market. At the extremes, if sigma is zero, there is no volatility, and the stock market portfolio becomes a riskless asset that earns the risk-free rate, like the risk-free bond from earlier. If sigma is extremely large, we can have two wildly different outcomes. I've provided visualizations of the possible stock market path movements, with the numbers introduced in the previous slides. We can use our model to figure out how much the guarantee component is worth in each scenario. If it goes up, the guarantee is worth 0. If it goes down, the guarantee is worth $5.94. We have two financial instruments to work with. We have the stock market portfolio and the risk-free bond. We can buy or short delta units of the stock market portfolio, and we can invest or borrow B dollars at the risk-free rate. There are two outcomes we need to replicate depending on what happens. We can express this mathematically with the following system of linear equations. The left-hand side describes our stock and cash positions in each scenario. You can see in the up scenario, we now own or are short delta units of the stock market portfolio that has gone up, and we've accrued interest on the B dollars. On the right-hand side is what we need to pay off in this scenario. With our actual numbers, you can see this reduces to a system of linear equations where we need to solve for delta and B. The solution is right here. Note the cost at time zero, therefore, is simply delta units multiplied by the value of the stock market portfolio at time zero plus our cash position. And the final cost to setting up our hedge strategy is $2.97. Let's summarize what just happened here with a list of transactions. For the sake of simplicity, I will be ignoring transaction costs and shorting margin requirements. At time zero, the client pays us $100 for the investment and $2.97 for the guarantee. We pay $100 for the share of the stock market portfolio through some stockbroker, and the broker gives us one share of the stock market portfolio. We then short 0.3564 shares and receive $35.64 from the short. Now we can invest $38.61 at the risk-free rate, $35.64 of which was received from the short, and $2.97 of which was received from the client's premium. Now, after 1 year, in the up scenario, this is what happens. we sell our share that's gone up and receive $112.75. We receive $40.18 from the risk-free investment and need to pay $40.18 to cover our short position. This $40 is from the delta units we shorted times the value of the stock market portfolio now. After this, we now have $112.75 to deliver our client. I should note, it's possible to simplify this list of transactions so that we only pay for 1 minus 0.3564 shares of the stock market portfolio, but I've broken out the long and short positions so it's clear what's going on. The list of transactions is the exact same for the down scenario with some minor differences. This time, when we sell one share of the stock market portfolio, we only receive $96.08 because we are in the down scenario. However, since the stock market went down, we only need to pay $34.24 to cover our short, and we still receive $40.18 from our risk-free investment. What we pay back the client then is $96.08 plus $40.18 minus $34.24, which comes out to $102.02. And this is the minimum required amount to pay back to fulfill our guarantee. You might come back to me and say, Gabe, this is a very simple model. This is not realistic. The stock market can have much more than two outcomes. And this is obviously true. And I want to build towards a more realistic solution. So let's do that. Let's add a time step in the path, and now we have three outcomes. While 3 is not much better than 2, we can approach a more realistic model as we add more and more time steps. I'm going to make a couple of adjustments to our U's and D's, and I'm going to introduce another variable called H, which measures how long each time step is. We multiply R by H because the risk-free asset would only be able to earn that amount of interest during the time step. We multiply sigma by the square root of H to dampen the volatility, as we expect the stock market portfolio's possibilities of movement to be less in a smaller time step. I'm not going to get into the details of why the square root of H, as this intuition is sufficient for now. We are in the same situation as before, where we can buy or short delta units of the stock market portfolio and invest or borrow B dollars at the risk-free rate, except this time we need to replicate 3 outcomes instead of 2. What can we do? What's different about this situation is halfway through the year, we see what happens to the stock market. We have the opportunity to change our position halfway through the year and react to what ends up happening. This is the key to dynamic hedging. Since we can change our position halfway through the year, let's consider what our position should be at that time. In each scenario, the problem reduces to the one-period tree problem we solved earlier. In the up scenario, the stock market has gone up. This is why you see the extra U factor in the left-hand side and right-hand side of these equations. We can simplify and solve, and we see that the cost of hedging is 0 in this case. Intuitively, this means that the stock market portfolio has gone up in the first period, and we know for certain, that is in this model, that the stock market portfolio will provide a return greater than 2%. In the down scenario, we have an extra factor of D in the necessary places in our equations, and the cost of hedging is $4.57. What should our hedge position be at the beginning? We need to match the payoffs of the cost of hedging in each scenario that occurs at t equal to 0.5. In the up scenario, our hedge cost was 0, and in the down scenario, our hedge cost is $4.57. We need to play the same game again and ask ourselves, how many units of the stock market portfolio should I buy or short, and how many dollars should I invest or borrow at the risk-free rate to replicate these payoffs? Mathematically, this is expressed in this system of linear equations. We can solve and figure out how many units we need to buy or short, and how much to invest or borrow at the risk-free rate. Our final position is on the slide, and our upfront cost is $2.30. On the right here, I've provided a visualization of the hedge cost tree. At the end is the dollar amount we need to have to provide the minimum 2% guarantee to our client. And in the middle is the cost of hedging in each scenario, as we solved for in the last slide. At the beginning of the tree is the cost of hedging initially. The tree provides a visualization of how much it costs to hedge at each time step. The main idea here is that we can react to changes in the market to dynamically hedge our risk. Here, our hedge position at time 0 will have payoffs equal to the cost of hedge at time equal to 0.5. Since we have a position at time 0 that will have payoffs equal to the cost of hedge at time equal to 0.5, we can finance the hedge we need no matter what happens to the market. Numbers here correspond to our example. I would encourage you to go through the calculations by hand as this forces you to understand what's going on here. I'm hoping that you're starting to get the idea that we are doing the same thing over and over again. The question now is, how complex can we get, and can we keep adding periods? The answer is yes, we can. You can see the diagram here. We can break our 3-period tree into 2 2-period trees and 1 1-period tree. The idea is that since we were able to solve the 1-period tree, we could solve the 2-period tree, and hence the 3-period tree and the 4-period tree, and so on. This means we can solve any period tree. The 3-period hedging table here corresponds to our example. This slide is to show that it can be done. We can finance our guarantee by reacting to what happens in the market at each time step. Let's try to approach reality now. In theory, the stock market portfolio can do any number of things, but the more time steps we add, the more realistic our model becomes. I've constructed here a 52-period tree, which is meant to simulate an up or down weekly movement. While the stock market can do any number of things, and can be any number of values at the end of the year, this tree captures a wide range of possibilities and describes a very plausible set of paths and outcomes for the stock market. For this animation, I've shown the cost of hedging for each tree that's passing by. As you can see, the cost of hedging fluctuates from around $2.30 to $2.20. As we get more time steps, it stabilizes around $2.26. This tree describes the cost of hedging at time 0 and what our strategy will be to finance our future hedges. The 2 key takeaways I hope you get away from this video are the answers to the key questions we asked at the beginning. The first takeaway is that to provide the guarantee, we construct a path of possible stock market movements, then solve for the position we need to take at each point in the path. This gives us the solution to how we can dynamically hedge our risk of providing the guarantee. The second takeaway that I hope you get is that through this process of solving for the cost of financing the hedge at each point in the path, we can figure out what we should charge the client. That is, we charge the client the time 0 cost of hedging. This is the fair price. Thanks to 3 Blue 1 Brown for hosting the Summer of Math exposition, which encouraged me to make this video. I'll be making a second part to this video, which backtests this method during the stock market crash of 2020 during the pandemic, so be sure to check that out. Thanks for watching.